To start this section, I'd like to remind you, take you back to Calculus 1, to a derivative. So let's think about, let's make a derivative up. Let's do the derivative of something like x cubed plus sine x to the 10th, let's say. So you think back to Calculus 1 and you remind yourself of the chain rule, and you say, really what I've got here is some stuff to the 10th power. And like any stuff to the 10th power, the derivative is 10 stuff to the 9th power, and you leave the stuff in here. So this is x cubed plus sine x. And then the rest of chain rule says, because it's not just plain old x to the 10th, we also need to look at how quickly the stuff is changing. So we multiply by the derivative of the inside, so that becomes 3x squared plus cosine x. And we're done. So here in Calculus 2, where we're looking at reversing these sorts of things, if we happen to have an integral that looked like 10 times 3x squared plus cosine x times x cubed plus sine x to the 9th. If we happen to have that exact integral, we would know how to do it because we just did the derivative that matches it. And we'd say, hey, that looks like somebody did chain rule. And I will undo chain rule. We'll unchain this problem. And it would go back to x cubed plus sine x to the 10th. And because this is an indefinite integral, of course, we will not forget our plus c. But let's suppose that you didn't just do the matching derivative. Or maybe you just don't recognize the pieces. Because even without doing the derivative, you could probably look at this and say, oh yeah, the pieces are there in this integral problem. But let's talk about how to undo the chain rule in general, and that's what's called the substitution rule. Sometimes called the u-substitution rule, although they really could have used any letter. But let's take a look at how the u-substitution rule works. To do u-substitution, you would look at your integral, your thing you're trying to integrate here, and you would hopefully find the piece that was originally a function inside of another function, right, that came from chain rule. And in this case, I would say we've got that right here. You could say, hey, there's some function inside of another function. And that inner function, so our whole goal is to pick out the inner function first. So that's going to be u. So I look at this one and I say, I think the u function was x cubed plus sine of x. And once you pick u, we also need to figure out the derivative of u. The derivative of u with respect to x. So this is kind of like a dy dx notation, except it's just du dx notation. And I don't need to look at the original problem anymore, at least for this step. I'm just saying, hey, I picked a u. Because of that, I have to go with this as being my du. And it turns out that we will typically want to multiply both sides by dx on this equation. So usually rather than writing it like this, let's take that dx out of there, multiply both sides by dx. So usually you'll see this expression just written from the beginning like this. And then you go back to your original integral and you say, hopefully I can substitute here. So let's rewrite the original integral. Say it's still the integral. 10 is still 10, parentheses. But then look at what's inside the parentheses there. This 3x squared plus cosine x. I have a replacement for that, and actually I need 3x squared plus cosine x and also the dx over here. Those two pieces together get replaced by du. So I'm going to say the 3x squared plus cosine x and the dx, all of that turns into du. So I'm just going to fill that in as du. And close the parentheses off. And let's keep going with our substitution. The next bit is parentheses. And inside those parentheses is x cubed plus sine of x, which happens to be u. So let's put u right there, and the rest of it is going to just be stuff that was already there. So the integral now looks a lot simpler. Granted, it's not quite in the order we normally like integrals to be in, so let me just shuffle the order a little bit and say I've got the integral of 10 u to the 9th and put the du on the end where we'd like to see it. Okay, this integral is one that's pretty easy for us to do. I mean, it's in u's instead of x's, but it's u is the variable the whole way, so we can just integrate this just like it was x. So we say, what is the integral of 10 u to the 9th du? And we know how to do that integration. The 10's even in the right spot, so we just integrate, and that integrates to u to the 10th plus c. And last step is to remind yourself that this problem, when we started it, was not a problem about u. It's never really about u, is it? Really is a problem about x. So make that final substitution and say u is really just a nickname for x cubed plus sine of x. So there's my u coming down there. So u to the 10th plus c. Okay, so that's the basic idea of u substitution. And I want to take a look at another one where the pieces don't match up quite so well. So let's try one more problem. And let's try maybe an integral. Let's see, let's get an x squared here. And let's get an x cubed plus 3 to the 5th dx. And again, this is two functions multiplied, and we don't have any other way to figure that out. None of our basic antiderivative rules work. But it does look like it's probably got a u substitution going on here. So I'm looking at this, and I see this piece inside of another function. So that seems like a pretty good candidate to be u. I'll try it anyway. Let's see. U is x cubed plus 3. And I just have to go with du then. Say the derivative of u would be 3x squared. And don't forget the dx on the end. So I'll go back and I'll try to rewrite my original integral. I'll try to make substitutions and see how that works. So I've got the integral, and I'm going to skip the x squared part for a second. So let me move over to this part and say what's inside the 5th is definitely exactly u. So that's great. I like that part. The only problem is what's left now is the x squared and the dx. And I have that right here, but there's that extra 3 hanging around. It's a small difference, but it's a difference, right? I can't replace x squared dx with, I'm not sure what it gets replaced with. But fortunately, this line right here is an equation. It's an algebraic equation, which means I can do a little algebra on it. And particularly, I'm going to divide both sides by 3, or multiply both sides by 1/3. Maybe that's a better way to look at it. So I'll multiply both sides by 1/3 and get 1/3 du is x squared dx. And notice x squared dx is exactly what I needed to still replace. So I will just, and this is typical of u substitutions, I'll replace, or I'll do algebra until I have a replacement for the stuff that I need. And hopefully I can do a little manipulation and get it there. Okay, so x squared dx, I found out I can replace both those pieces with 1/3 du. And the key with u substitutions is to make sure you don't have any x's left over. And I've turned everything into u, so I need my integral to be in one variable. And again, it's a little bit out of the order that I normally like, so let me do 1/3 u to the 5th du. And now we're in pretty good shape to integrate. I know the 1/3 is just going to sit there, so let's integrate and say this is 1/3, and u to the 5th, that goes to the 6th, and you get a 1/6 right there. And of course you get a plus c on the end. And that's really basically done. I need to clean up my fraction. So 1/3 times 1/6 is 1/18th, and I'm also going to make that back substitution because it's not about u. So u is x cubed plus 3 to the 6th, and I'm going to keep that plus c on there. Okay, so there was an example where the u and du didn't match up perfectly to start with, but I was able to do a little bit of algebraic manipulation and get to the final answer. Okay, so we'll look at a couple more examples in the next video.